In the last video, we solved second or higher order homogeneous linear equations with the constant coefficients. Now in this video, we'll be taking a look at how to solve second order or higher order homogeneous linear equations with variable coefficients. We'll begin this section by discussing Cauchy-Euler equation. A linear differential equation of the following form is called a Cauchy-Euler equation where A and the other terms like this, and this are constant coefficients, and the powers of x decreases with each successive derivative. The key characteristic of this equation is that the degree of x in each term matches the order of the derivative. So you can see that the power of x here is n, and its derivative is also n. Similarly, for the next term, for x power n minus 1, we have the order n minus 1. This is why it is also called equidimensional equation, because the dimensions or the powers of x are consistent with the order of differentiation. Let's consider a standard second order ordinary differential equation. Here, a, b, and c are the constants. You can see that x squared is paired with a second derivative, x with the first derivative, and y, which is effectively x power 0, has no derivative. This matches the structure of the Cauchy-Euler equation. To solve these types of equations, we convert it to the simple algebraic equations. To do that, we need to eliminate the variable x here and here. So if you're going to assume that the solution of the form y is equal to x power m, then you're going to be taking its first and second derivatives. Substituting these into the original differential equation cancels out the terms x, and we are left with a characteristic equation. So let's do that. You can see that x to the power of m is common in all three terms. So if you're going to factor this out, and we are going to be left with this equation. You can see that the bases are the same. So the powers are going to add, and this is going to cancel out this. This is going to cancel out this. So let's write our auxiliary equation in simplified form. But before that, let's try to solve this equation. We know that x power m is being equated to 0 here, and this entire thing is also being equated to 0. However, since y is equal to x power m is a solution of this Cauchy-Euler equation, the x power m cannot be equal to 0. So we're only left with this. And to write this in simplified form, I'll be getting this auxiliary equation. Now, if you're going to be solving the auxiliary equation, you'll encounter three different scenarios. The first, where the roots are going to be real and distinct. For that, we are going to be using this equation to find the general solution. The second is where the roots are real and equal. For that case, we are going to be using this equation to find the general solution. And for the third case, where the roots are complex conjugates, we'll be using this equation to write our general solution.